0.1 millimeter. That's the margin of error in stone joints carved high in the Bolivian Andes, more than 1,000 years before the Inca Empire even existed. At Baalbek, a single foundation stone weighs over 1,000 tons, hauled 900 meters from its quarry by methods no modern engineer has conclusively explained. And at Gobekli Tepe, hunter-gatherers who had not yet invented agriculture raised monumental pillars 12,000 years ago. 7 ancient buildings that predate the very technology required to build them by thousands of years. So, what did these builders know that we have forgotten? High in the Bolivian Andes, scattered across a windswept plateau, lie the shattered remains of Puma Punku. Archaeologists first measured the site's iconic H-shaped blocks, expecting rough stonework typical of a pre-metal age. Instead, they found something that defies all ordinary explanation. Stone joints so precise, showing extraordinary precision, that in places a human hair barely fits between them. Laser scans and photogrammetry have now confirmed what earlier explorers could only guess. Across dozens of blocks, the deviation between adjoining surfaces averages less than 0.15 millimeters. Some joints hold to a tolerance of just 1/10 of a millimeter, numbers that rival the calibration of modern machinists, let alone ancient stonemasons working without steel tools. The blocks themselves are no mere pebbles. The largest verified monoliths at Puma Punku weigh in at 85 to 130 tons. Popular myths inflate these figures to 450 tons, but every scientific survey puts the true maximum far lower. Still, a single block outweighs a fully loaded semi-truck. The question is not just how these stones were moved, but how their faces were rendered so flat and their corners so sharp that even today's laser-guided equipment would struggle to improve upon them. The puzzle deepens when examining the material. Most blocks are andesite, a volcanic rock harder than steel's earliest forms. Some researchers have proposed that the builders didn't just carve these stones, they may have cast them. Laboratory analysis of certain blocks hints at a geopolymer binder, a kind of ancient concrete made by mixing volcanic ash with lime and sand, then pouring the slurry into molds. Cast or carved, either method demands a level of material control and planning that seems out of reach for a first millennium civilization. Yet the evidence on the ground resists easy answers. Thin section microscopy of the andesite shows natural crystalline structures, matching local outcrops on the Copacabana Peninsula. The absence of clear polymeric residues inside the hardest blocks keeps the geopolymer theory in limbo. Experimental archaeology has managed to reproduce some of Puma Punku's tolerances using nothing but stone hammers and abrasive sand, but at the cost of hundreds of hours of labor for a single edge. Tool marks tell their own story. Under magnification, the edges bear parallel striations, signs of relentless grinding rather than chisel blows or metal saws. No copper or bronze tools have been found at the site, and attempts to replicate the blocks with copper chisels have failed to achieve the same crispness. The builder's toolkit remains a mystery, as does the full extent of their knowledge. To this day, debate rages in scholarly circles. Was Puma Punku's perfection the result of a lost casting formula, or simply the outcome of patience, ingenuity, and techniques now forgotten? The only certainty is the measurable result. Stone blocks shaped and joined with a precision that still provokes awe, and a method that no one has yet managed to fully explain. The enigma of Puma Punku stands as a silent challenge, an ancient question carved in stone that continues to defy the limits of our understanding. At Baalbek, in the Bekaa Valley of Lebanon, 3 limestone blocks, together known as the Trilithon, rest at the heart of a platform that dwarfs even the largest stones of Puma Punku. Each block measures nearly 19 meters long and weighs between 800 and 1,200 tons, according to recent gravimetric surveys. The sheer mass is staggering. A single trilithon outweighs the heaviest modern construction crane's safe lifting limits. Yet these stones were not left in the quarry. They were moved, somehow, from a hillside nearly 900 meters away, and set with such accuracy that the platform remains stable after 2,000 years. No ancient text describes the full process. What survives are clues. LiDAR scans of the terrain reveal a corridor sloping gently from the western quarry to the temple mound, interrupted by shallow depressions that may have once supported ramps or staging platforms. The quarry floor sits just above the temple's elevation, suggesting the builders could take advantage of gravity. But even with a downhill grade, the logistics seem to strain credulity. Roman engineering manuals, like Vitruvius's De Architectura, describe the use of capstans, wooden cranes, and lever systems. These texts mention the polyspastos, a kind of compound winch that could, in theory, multiply human effort. But no known Roman machine could handle a load of 1,000 tons. The largest Roman cranes topped out at around 100 tons, barely a tenth of the trilithon's mass. Experimental models show that an earthen ramp, lubricated timber rollers, and a sledge could move such a stone, but only with a workforce of thousands, coordinated with a precision that defies the written record. Some researchers propose a radical alternative: water flotation. The plateau's limestone bedrock supports the idea that temporary canals could have been dug, flooding the route between quarry and platform. Submerging the blocks would reduce their effective weight by nearly a third, making the impossible at least marginally plausible. Simulations suggest that a block floating on a wooden pontoon in a shallow canal would require far less force to move than dragging it overland. Yet no direct archaeological evidence of such canals survives, and the debate continues. LiDAR mapping has uncovered micro-depressions on the temple platform that correspond precisely to the trilithon's base, hinting at a controlled sinking or placement method. Toolmark analysis on the stones themselves reveals mostly low-angle striations, consistent with stone-on-stone abrasion, not metal chisels. The absence of Lewis holes used for lifting with iron tongs raises further questions. Did the builders rely solely on gravity and leverage? Or did they possess lifting devices now lost to time? No modern construction site has attempted to move a monolith of this size by hand. Even today, the largest mobile cranes and heavy-haul vehicles would struggle to replicate the feat without disassembling the block. The trilithon's journey from quarry to platform remains a logistical riddle, a challenge that pushes the boundaries of ancient engineering and leaves us wondering whether we have underestimated the ingenuity or the forgotten knowledge of those who came before. Sacsayhuamán rises above the city of Cusco, its walls a fortress of interlocking limestone giants. Some of these blocks tip the scales at nearly 200 tons, each one shaped and placed so precisely that the joints rarely exceed 2 millimeters. This is not the casual fit of fieldstone or the rough stacking of boulders. Instead, laser scans reveal faces aligned so closely that a modern engineer would recognize the tolerances from a prefabrication manual. The zigzag pattern of the outer walls, with their wild, irregular polygons, looks almost chaotic at first glance. But beneath the surface, a different story unfolds. Finite element models have subjected these walls to the same seismic forces that have toppled every colonial building in Cusco over the past 5 centuries. The simulations show that the complex, inverse V plan, where walls lean inward at more than 30 degrees, channels earthquake energy along the seams. Instead of cracking or collapsing, the blocks shift minutely, dispersing shock waves through countless friction points. The plus or minus 2 millimeter joints act like dry friction dampers, absorbing energy and preventing catastrophic failure. During the devastating 1950 earthquake, the colonial city crumbled, but Sacsayhuamán's massive stones barely budged. No mortar holds these blocks together. Each face must have been trimmed, checked, and retrimmed until the fit was exact. The labor is hard to imagine. Shaping a 200-ton stone so that it nestles perfectly against its neighbors, its surface undulating to match the next with almost no gap. Was this the result of trial and error, or did the builders possess a deeper understanding of geometry and force? The evidence points toward intentional design, an ancient strategy for survival in one of the world's most earthquake-prone regions. Today, the polygonal walls stand as a living model of adaptive engineering, their resilience confirmed not just by history, but by the numbers in a modern seismic lab. Rising from a shallow lagoon on the island of Pohnpei, Nan Madol is a city built entirely atop the sea. Over 90 man-made islets, assembled from nearly 250,000 tons of basalt, form a network of platforms, courtyards, and ritual enclosures. But the true marvel lies beneath the surface. LiDAR mapping and GIS bathymetry have revealed a grid of ancient canals, some now silted in, that once threaded between the islands, evidence of a civilization that engineered not just buildings, but the landscape itself. Transporting basalt columns, some weighing as much as 30 tons, across open water without wheels or beasts of burden poses a logistical riddle. The nearest confirmed quarry sits nearly 25 kilometers away at the foot of a volcanic plug. Archaeological studies, backed by isotope fingerprinting, have matched the stones of Nan Madol to this distant outcrop. How did the builders move such massive cargo through the lagoon's tangled channels? Experimental archaeology offers a clue. Modern crews, using bundles of hollowed logs lashed together, have demonstrated that a log raft can support a 50-ton basalt block in just 1.2 meters of water, the same average depth measured along the ancient canal routes. With a drag coefficient of 0.1, a team of 12 to 15 paddlers can maneuver a fully loaded raft at a steady pace, matching the demands of large-scale construction. Anchor holes cut into the stones suggest a system of rope tensioning, allowing blocks to be stabilized and guided into place. The scale of this operation is staggering. To build Nan Madol's artificial islets, generations of workers hauled and set hundreds of thousands of tons of basalt, one raft load at a time. Each new islet was raised on a platform infilled with coral rubble and volcanic ash, then ringed by basalt columns stacked in crisscross patterns. The canals themselves doubled as transport lanes and storm drains, a design visible only now through LiDAR surveys. Without the wheel, without pulleys, these builders mastered a maritime solution, reshaping land and water into a city that still defies the imagination. On a gentle rise above the River Boyne in Ireland, Newgrange stands as a silent clock built from earth and stone. Radiocarbon calibration curves place its construction at 5,200 years ago, predating the pyramids of Egypt. Yet the true marvel hides within its passage, a tunnel that runs deep into the mound and points with uncanny accuracy toward the winter solstice sunrise. Surveyors have measured the entrance azimuth at 131 degrees, with a margin of error less than a third of a degree. That is not an accident of rough alignment or a lucky guess. The builders shaped the passage to rise at just over 12 degrees above the horizon, matching the sun's slow climb on the shortest day of the year. Each December, as the solstice dawn breaks, a thin shaft of sunlight slips through a narrow opening above the entrance, known as the roof box. The beam travels nearly 19 meters down the stone corridor, illuminating the inner chamber for exactly 17 minutes. Not 16, not 20, but a window so precise that even a slight deviation would have left the chamber in shadow. High-speed video and light tracking confirm this alignment has held steady for millennia, despite the slow drift of the Earth's axis. The feat demands more than simple observation. To achieve this, Neolithic architects had to understand the solar cycle, the tilt of the land, and the shifting position of sunrise across the year. They had to calculate the azimuth, design the passage's slope, and place every stone with the solstice in mind. The numbers leave little room for doubt. A 131-degree axis, a 17-minute illumination, and a construction date confirmed by 19 independent radiocarbon samples. Were these ancient builders astronomers, engineers, or something else entirely? Newgrange's silent chamber still answers the sun each winter, its light tracing a calendar older than history itself. But nothing prepared archaeologists for what surfaced on a hilltop in southeastern Turkey. At Gobekli Tepe, radiocarbon dating of charcoal and animal bones placed the first stone circles at nearly 12,000 years before the present, millennia before the rise of agriculture, cities, or metal tools. The site's T-shaped limestone pillars, some weighing up to 10 tons, were not only quarried and carved by hand, but then arranged in massive circular enclosures. Yet the most staggering revelation came not from the stones themselves, but from the earth that hid them. Excavators uncovered a layer of sterile backfill, tons of clean, stone-choked soil, deliberately packed to bury the entire site around 8000 BCE. Stratigraphic analysis and AMS radiocarbon dating of the fill confirmed that the burial was not the work of time or nature, but a calculated act by the builders themselves. Micro-wear studies on flint tools found in the fill reveal percussion marks and abrasion patterns, evidence of a toolkit still rooted in the Stone Age. If these hunter-gatherers could organize labor on such a scale, what else did they know? The deliberate burial of Gobekli Tepe raises questions that ripple across the story of civilization. Why would a people with no settled villages build the world's earliest monumental sanctuary, and then hide it beneath a man-made hill? The answers, still locked in the layers of backfill, challenge everything we thought we knew about the origins of complex society. On Easter Island, the challenge was not just carving the moai, but moving them, some weighing as much as 86 tons, across rugged terrain with no wheels, no draft animals, and limited timber. For years, the logistics seemed impossible. Then, a team of 30 researchers and volunteers tried a different approach. Instead of dragging the statues on sledges or rolling them on logs, they stood a replica upright, tied ropes to its sides, and rocked it back and forth. With each coordinated tug, the statue shuffled forward, pivoting on its curved base. In a matter of minutes, the crew advanced a 30-ton replica nearly 10 meters, using only human power and simple ropes. Force gauges measured the load at each step, confirming that the rocking method kept the statue stable and required less effort than traditional hauling. Microscopic analysis of ancient trailwear revealed matching patterns, side-to-side abrasion rather than straight-line grooves, corroborating the feasibility of this method. The experiment demonstrated that with nothing more than ingenuity and teamwork, ancient islanders could have walked even the heaviest moai across the landscape, solving a riddle that had stumped generations. In 84 BCE, a Roman shipwreck off Greece yielded the Antikythera mechanism, a corroded cluster of bronze gears mapped by CT scans to reveal astonishing precision. Some gears, just fractions of a millimeter apart, tracked eclipses and planetary cycles. That technology remained unmatched for over 1,000 years. In Roman harbors, concrete piers have resisted the sea for centuries. Only recently did electron microscopes uncover their secret, a matrix of calcium aluminum silicate hydrate, known as CaSH, that grows and seals microcracks when touched by seawater. This self-healing chemistry, born from volcanic ash and lime, has outlasted modern marine concrete. Damascus steel, forged in ancient Syria and India, was famed for its strength and patterned sheen. Transmission electron microscopy now reveals nanoscale carbide layers less than 100 nanometers thick woven through the metal, a technique lost to time. In Han Dynasty China, Zhang Hing's earthquake detector appeared in 132 CE. The bronze vessel, ringed with dragons and toads, could sense tremors from 500 kilometers away. Mechanical trigger analysis confirms its sensitivity. relying on mass inertia to release a ball toward the quake's direction. Across continents, ancient minds engineered mechanisms and materials that challenge our assumptions about the limits of early science. Today, laser surveys still struggle to match the precision found in stones shaped over 4,000 years ago. As ground-penetrating radar uncovers new secrets beneath ancient foundations, each discovery deepens the enigma, challenging what we think we know about human ingenuity. The question isn't how these feats were achieved, but what knowledge we may have lost. Some mysteries aren't buried in the past. They are waiting beneath our feet. Share your thoughts below.